Hi, my name is Hiromichi AKIMOTO. This video is the introduction to our new concept of marine current turbine. Because the output of tidal current and ocean current are predictable, they are useful in the mixing with existing power resources. However, the cost of energy produced by marine current is still expensive, because R&D of submerged device is expensive. It requires transmission from offshore site to onshore, and maintenance cost is also high. It is because the devices are submerged in seawater, so the access is not easy. And we have to remove biofouling on the surface of the turbine blade. But in East Asia, where the water temperature is higher than in Europe and other countries, the biofouling rate is 8 centimeters per year. So the cost of maintenance is very significant. In the concept of Shigen, they are providing elevator system to lift up turbine for easy maintenance access. In open hydro, they are using fluid lubrication by seawater to reduce the frequency of required maintenance. So they are trying to reduce the cost of maintenance. Other problem is high weight-to-power ratio of marine current turbine. Because the density of water is much higher than that of air, the turbine experiences very high hydrodynamic load. So the supporting structure is much larger than the wind application. Our solution is a flexibly supported vertical axis water turbine. In this design, the axis of the turbine is not in the fixed upright position. Power takeoff system is on the axis and above the water surface. In this design, the inlet shaft of power takeoff system is free from high bending moment, so it can reduce the cost of the device. In conventional installation of vertical axis turbine, people need very rigid supporting structure. In comparison to this conventional installation, our design can reduce the supporting structure significantly for the low cost of power generation. Also, in this design, the submerged part can be lifted up to the water surface for easy maintenance access to the hydrodynamic blade. Also, we can expand the swept area of the turbine easily in water depth direction. We proposed floating axis wind turbine. This is a flexibly supported vertical axis type wind turbine. By a flexible support system, we can minimize the support structures. This support system can be also used in the present marine current turbine design. The technology is same as floating axis wind turbine, and power takeoff system can be installed above the water surface. Also, this design will provide the easy maintenance access to the submerged part. Reduction of weight-to-power ratio is important in marine current turbine. This is an existing concept of vertical axis tidal current turbine. As you can see, the floating system is much larger than the turbine itself. This is a bottom fixed type tidal current generator. Also, the turbine size is much smaller than the supporting structures. In the proposed design, the turbine is the main part of the total system. So we are deducing the supporting structures. In ocean engineering, cost of the device is almost proportional to the weight of the device. Therefore, weight to power ratio is proportional to the cost to energy ratio. So it is equal to the cost of energy. So for economic performance of the marine current turbine, we should seek the condition. Turbine should be the main component of the system. Support system of the turbine shaft is the same as previous offshore wind turbine application. The weight of power takeoff system roller generator units are supported by a small float surrounding the turbine shaft. Power takeoff system is similar to the regenerating brake system of electric vehicle, and the turbine shaft is self-buoyant. This design provides easy maintenance access to the submerged blades because it can be lifted up to water surface by discharging ballast. Also, the design is applicable to tidal current power where the direction of water flow will change in time. This is an example configuration of a tidal current turbine. The assumed power is 139 kilowatt in flow speed of 2 meters per second. The turbine size is 6 meters in diameter and 25 meters in height. The larger application will be ocean current turbine. In the world, there are some stable ocean currents like Kuroshio and Gulf Stream. Especially in Kuroshio ocean current, it is very close to highly populated area of Japan. The observed high current speed is up to 2.5 meters per second. This is an example configuration of ocean current turbine. In this design, two counter-rotating turbines are connected for cancelling the reaction torque of electric generators. The size of the turbine is 12 meters in diameter and 46 meters in height. The rated power is 1 megawatt each in 2.5 meters per second current speed. Because the infrastructure of transmitting electricity to onshore is expensive, we have to consider ocean current farm. In this image, there are 60 units of twin turbine, and estimated cost of energy is competitive with shallow water bottom fixed wind farm. We estimated the total operational cost of the marine current turbine in the farm. About 90% of the cost is capital cost, and about 1/3 of capital cost is for the device of marine current turbine. Another 1/3 is electric transmission, and the remaining 1/3 is for mooring and anchoring. The total cost of energy is still competitive with offshore bottom fixed wind farm. This ocean current turbine is very compact in comparison to floating wind turbine. However, the drag force acting on the marine current turbine is very high because of the high density of water in comparison to air. Therefore, if we use high quality mooring of ocean plants, it is not easy reducing the cost of energy is not easy. In ocean current turbine, there is no passengers nor chemical materials. Therefore, we can use low-cost moorings. If we can have low-cost mooring specialized in ocean current turbine, we can enhance the economic performance of this device. The conclusion of this presentation is as follows. We introduced flexibly supported vertical axis marine current turbine. In this design, the power takeoff system is free from high bending moment and installed above the water for reducing the cost of the device. Swing mechanism of the turbine shaft will provide low cost and easy maintenance access to the submerged blades. We can use the support system of the previously introduced floating axis wind turbine. Estimated economic performance of ocean current turbine is competitive with the wind farm of bottom fixed turbines. Cost reduction may be possible by introducing low-cost mooring specialized in the ocean current turbine. Thank you for your kind attention.